Alright, I'm not sure which recording attempt this is now, but here's lecture 10. We're going to go through the example that we introduced last time, which we have a satellite with an altitude of 600 kilometers over the Earth, 20 degrees of the true anomaly past the zenith of the ground station. The elevation's at 4.3 degrees from that ground station, and then the eccentricity, so it's a circular orbit in posigrade, and the inclination is 0 because it's an equatorial orbit. So we're going to cover that today. So let's go ahead and get started. So lecture 9 is posted. There are the notes. There's the link to them. Again, questions if you have them, post them on the YouTube page. The only thing we're going to be covering today is the example. So the examples for range and range rate, we're going to cover two-way ranging so that we can calculate, or so that we can cancel out the contributions of the atmosphere from the troposphere and the ionosphere. And then for the range rate, we're going to consider a transmitter beacon operating with 24.25 gigahertz. The code for the solution is in MATLAB. It's on GitHub. There are a few issues with the code right now that I'm working, but I'll identify them to you in the problem, and you'll be able to implement the solutions on your own. So, two-way ranging. So we want to determine the ideal range. The first thing we want to do is determine the ideal range between the ground station and the satellite. So in order to do that, we have to figure out our geometry. Well, we know that the zenith direction of the ground station, if blue is the zenith direction of our ground station, then that satellite's 20 degrees past that zenith direction. But the elevation is at 4.3 degrees, which means that the ground station is not going to be on the equator. It's going to be either elevated or projected at a different point in order to actually make those angles work, because the 20 degrees is going to go down to where the satellite is, or up, depending upon your orientation. And then the 4.3 degrees is just an elevation angle, is just with respect to the plane that the ground station makes with the local horizon. So we got to figure out our geometry. So we figure out that the, and I just cancel out the magnitudes here. We figure out that the latitude or the inclination of our ground station, so the latitude of our ground station is either 19.55 degrees or negative 19.55 degrees, depending upon your orientation. And in this case, I just assume that the longitude is 0 to make life easier on ourselves, and then we can find the ideal range at that point in time when the first beacon is transmitted from the ground station. So the signal arrival at the satellite, the signal arrival time, is unknown. So remember that process that we walked through in lecture 9 on how to do two-way range? We're going to do it right here. So we find the instantaneous range at time t. So when it's transmitted, which is the ideal range, what we just did, then we're going to find the signal arrival, which is basically just taking that signal, how far it has to propagate, so range over the speed of light, plus the time it was transmitted. So we find the time of arrival. Then we find a new range at that time of arrival and the updated position of the ground station. We compare the two, and we find our difference. So essentially we can, and then we're going to compare it to the round trip range that we would have received from an observation. Oop, I did not mean to shoot forward on that one. Yeah, but we can estimate by having the instantaneous range and accounting for the speed of light. And so that's what we see, what we do with the time of arrival. It's what you can do with an altimeter. So the Topex Poseidon, if you were using that as a case example, you would go to that altimeter and then you would use basically the average of the round trip in order to try and in order to try and give an estimate. And so it's the same thing that we do in step 2 of the problem. So the expected answers are on this magnitude. There is an issue because if you notice, my dot products, I don't actually include the magnitudes, but we divide them out. We'll run into some issues that I identify on GitHub with this, where the range isn't exactly the same depending upon the longitude that you choose. So something to keep in mind. So for the range rate, we know that the satellite transmits with a known frequency. We're going to receive that signal, and then we're going to mix it with some reference frequency. And in our case, we're going to choose to make the reference frequency the transmitted frequency to ease solving out the apparent frequency. And so what we do is we have some receiver that counts the number of cycles between the first signal received and then TR2, which could be the last signal received, or just some time that we choose for the next received signal. So we solve out, and that's our Doppler count, is that receiver, is literally what it's measuring. So we solve that out for our range and for our range rate. So you can see at the bottom there that we solve out for our range rate. Obviously it's not our instantaneous range rate because it starts to become an instantaneous range rate as the time difference in the transmitted time approaches 0, but that's never going to be the case. So it's a real range rate in some sense of the word. But our received frequency is going to depend on that range rate, as you can see below. So we have our Doppler count divided by the difference in the time transmitted, and it's dependent upon that range rate. Really, it's the difference, and so that will change where you'll see as the satellite approaches the ground station, like if this were our transmitted frequency, the received frequency will be higher as it approaches, drop down to the transmitted frequency, and then be lower as it leaves. And this is the example that everybody always makes, is an ambulance siren or a police siren. As it passes by you, the pitch changes depending upon its location relative to you. It's the same concept. So if we decide that, like GPS, our time difference in transmission is 1 millisecond, so start of GPS transmission, the pseudo-random code that's transmitted onto the first transmission, or the course acquisition code, 124 bits transmitted every 1 milliseconds. So we're going to just use that as an example to kind of work you into setting up something for GPS. We get our Doppler count, we get out a received frequency using the same equations that we had on this slide. And when we calculate that out based on where we currently are, we see that the received the apparent frequency is greater than the actual frequency. And so if we remember from our Doppler plot here, that means that we should be approaching the ground station. So the range estimate that we provide there, obviously that is a little bit different than the range estimate that we provided using the two-way range. So we know that there might be some issue that occurs there, especially when we see that our apparent frequency is 133 and our received frequency is 109 gigahertz. So there are some issues that need to be resolved. That's going to be solved in GitHub, but the basic concept of how to set this up is the same. This is the same math that you would use. You're just looking to use that range rate, and this is the ideal case, of course, right? Because we haven't considered propagating through the troposphere or propagating through the ionosphere. But and we've actually assumed that we don't have clock errors, even though for range rate, right, we only use one-way measurements. So we're going to have a clock error from not only the transmitted time, or from the transmitter, but also from the receiver that we have to consider, right? So it's the same way to set it up. There are some issues here which I'm going to go back and work through, and so that'll be available on GitHub. But for right now, I figured this was a decent enough example to go ahead and show you, kind of illustrate how this works. And so our lecture today is very quick, just because we're covering that example. And what we'll follow up with are the propagating through the troposphere, the ionosphere, the actual noise that we need to consider, especially time and things like that, that you would want to consider in a real measurement, or a real, depending upon how much reality you want to inject into your simulation, the type of models that you would need to consider. So, and that's what we'll follow up with for lecture 12. So, hopefully this lecture recorded this time. So, and I'll have it up to you by the end of the day. So, thank you.